Okay, so now maybe you're thinking how researchers in deep learning can think about this super complex architecture. I just showed you the inception architecture. How is it possible that a programmer will look at the data and say, probably the inception architecture is the best to learn this task. Maybe the inception architecture is the best hypothesis class to learn from this data. How can we have the intuition to create such model? And in fact, I think that there are some design patterns that are emerging in the literature. There are some patterns of how to combine modules together that people are reusing again and again to do their search of the best architecture for different tasks. So we will see some of the patterns that I saw very often in the literature. I enumerated some here, and we won't see some of them. Some of them will be covered in other lecture, but we will see at least these few first here. So the encoder-decoder pattern. So here there will be an encoder and a decoder. In each of these modules, there can be a lot of modules, a lot of complexity. But the overall architecture will be two components. So one encoder that will produce what we call the latent representation Z. And we will give this latent representation to a decoder that will predict a response. That will give me my prediction. Remember that the data can be in a high-dimensional space. So this latent representation will very often be in a lower dimensional space, will be in a vector that is much smaller than the vector as the input of the architecture. So this pattern encoder-decoder is used by autoencoder. It's really the definition of the autoencoder. It has been used also for sequence-to-sequence by a recurrent neural network that you will see on Thursday. And in Vision, you can see also encoder-decoder network, and you will see the U-net. And when you see the U-net, try to see the encoder and the decoder pattern in this image. You will see it tomorrow with Jeremy. So the autoencoder, it's a very old model in the literature. It's a model to do unsupervised learning. So here I don't have any labels. I just have, as an example, images. And what I want to do is to try to find the low-dimensional manifold that I was talking before. So I start with this image in a high-dimensional space. I give it to an encoder that will be a dense module with activation functions. And it will project this image to a small representation. And we will call it the code that encodes all the information that can be, all the factors of variation that I can move to change the image, but still by keeping the object in the image. It was the purpose of this architecture. So if I have a cat, I want to maybe change the value of Z2, and it will change the cat, but I will still have a cat in the image. This is what I want to learn with this model. Then I will give the code to a decoder, and the decoder will generate the same image as the input. And here the teacher will say that this is the real image, this is the prediction, so I can use a loss function that will compare the two, the reconstruction of my original image and this image. And I can use this feedback to train the model to reconstruct well. The code must be in a smaller dimensional space. It's like a bottleneck, because if I go from let's say 1,000 dimension, and I go to a vector of 10, and then I try to reconstruct my 1,000 dimension vector, the 10 dimension will be a bottleneck. It must contain all the information required to reconstruct the image. So that's why my image is not perfectly reconstructed. But by doing so, we hope to find the low-dimensional manifold. However, encoder doesn't work very well. This vanilla version doesn't work very well. There are variants of autoencoders that work much better, but they are outside of the scope of this lecture. But autoencoders are still a very active field of research because of this interesting pattern for the architecture. Also, we can have multiple input encoder-decoder. So let's say I have different information flows, one for encoder 1, one for encoder 2. I will have this pattern where all my flows will be associated to a branch in my network, and all these branches will provide me a representation. Then I will try to merge this representation, to aggregate them, and I will give it to a decoder that will predict the response. So I can process different modalities. Here I can have sound and images, and I want to predict something from 2 different modalities. I can also do metric learning, so I can give 2 images and try to learn the distance between the 2, if they are similar or not. And more generally, I can do relation learning on any kind of data. If the encoder, if the 2 encoders are able to process text, I can now compare 2 documents with this kind of architecture. So as a simple example, here, this encoder will encode my photo of a cat. Here, this encoder will encode the audio related to it. So let's say I have my task is that in my apartment, I have cameras and microphone, and I want to predict what is in my apartment. So the response would be one of the many concepts I have in my dictionary. I can process these 2 modalities with these 2 encoders, merge the representation, so it can be only a sum of the 2 representations that will be given at the output here. I can concatenate the 2 vectors together. I can do different operations to merge the 2 representations, and I will give it to a decoder that will then do the prediction. And I can train this model to recognize objects from visually and from the audio. And if I remove this decoder and I retrieve the representation of the 2 encoder, if I train it correctly, it made sense to compute distances in this space. Because it's like I'm taking 2 modalities and I'm projecting the 2 inside this common space. And since they are trained to, so that the audio related to a cat and an image related to a cat will be closer, I can compute distances, and I can build a search engine where I can say, give me the sound the most probable associated to this cat. And by just computing the distance in this latent space, I can recover this data point, and I will say this is the sound that is the most probable with this image, and the other way around. So with this kind of architecture, we can do powerful things in terms of comparing multi-modal data.